from West Virginia Public Broadcasting.
Support for the following is provided by the West Virginia Department of Education and West Virginia Public Broadcasting.
Hey everyone, it's Education Station, the show where we invite teachers from all across West Virginia to submit videos of themselves teaching their favorite lessons. In today's episode, we've got 3 exciting lessons about math, text features, and science. Well, hello and welcome back, everyone. I'm your host, Alex Milanese, and before we begin our first segment, I wonder if you can tell me anything that is similar between these 2 scenes. Well, for one, a carpenter and a baker both need to use fractions every day. So we're kicking off today's episode with Miss Denise, who has a helpful lesson about multiplying fractions. Let's check it out.
Today we're going to do math lesson 5. This is on multiplying fractions. We've looked at what fractions are. We've looked at the least common denominator. We've also looked at adding fractions and subtracting fractions. So now we're looking at multiplying fractions. So there are 3 simple steps to multiplying fractions. First, we have to multiply the numerators. Those are the numbers on top. Then we have to multiply the denominators, the numbers on bottom. And then we have to simplify the fraction if we need to. So let's look at an example. We're going to multiply 1/2 times 2/5, right? So step 1, we have to multiply the numerators. So here's our 1/2 and our 2/5. So over here we take 1 times 2, and that equals 2. So now we have a new numerator for our answer. So then we have to move on to step number 2. Step number 2, we're going to multiply the denominators. So here's our 1/2 times 2/5. So 1 times 2 is 2. And then if we multiply the denominators, 2 times 5 is 10. So the answer to our question of 1/2 times 2/5 is 2/10. But then we have to do step number 3. Step number 3, we have to simplify the fraction. We can reduce 2/10 to 1/5 because 2, divided by 2 is 1, 10 divided by 2 is 5. So 2/10 equals 1/5, and that would be our final answer. Okay, so I have another example. Let's try and see if we can remember the steps. 1/3 times 9/16. So we're going to multiply the numerators. Here are our numerators, the numbers on top. 1 times 9 is equal to 9. Then we're going to multiply our denominators. So we already have our 1 times 9 is equal to 9. We're going to multiply the 3 and the 16, which is equal to 48. So 9/48 is our answer. Can we simplify that? Yes, we can. So we can come down here. We can simplify this by, if we have 9/48 is equal to 3/16. All right, let's see what else we have here. All right. What we also want to look at is fractions and whole numbers. Can we multiply a fraction by a whole number? Yeah, we can do that, but the first thing we have to do, if we have in our example number 1 under whole numbers, if we have 2/3 times 5, we have to change 5 into a fraction. So the easiest way to do that is just to put it over 1. Anything over 1 is that number. Even if we had 100, 1,000, 1,000,000, it would still be that same number. So 5 over 1 is equal to 5, so we're going to change it to a fraction. Then we just proceed as we normally would. We have our 2/3, which we brought down from up here. Here's our 5 over 1. What is the first thing that we have to do? We have to multiply our numerators. So 2 times 5 is 10. Then we have to multiply our denominators. 3 times 1 is 3. So if we're going to leave this, this is top heavy, but we're going to leave it in this form because it didn't tell us to change it into a mixed number. So we're going to leave it as 10/3. Example number 2, we have 3, which is our whole number, and we're going to multiply that times 2/9. So what did we do the last time? Up here we put 5 over 1. We can do the same thing with 3. We can make 3 into 3 over 1, and then we can proceed. So we bring our 3 over 1 down here, and we're going to multiply it by 2/9. Step number 1, we multiply the numerators. 3 times 2 is 6. Step number 2, we multiply the denominators. 1 times 9 is 9. So our answer of 3 over 1 times 2 over 2 ninths is equal to 6 over 9. Can we reduce that? Yes, we can. We can simplify 6 ninths into 2 thirds, because 3 will go into 6 2 times, and 3 will go into 9 3 times. So our final answer would be 2 thirds. All right, let's look here. We also want to look at multiplying mixed fractions. So a mixed fraction is a whole number with a fraction with it. That's mixed fraction. We're mixing a whole number with a fraction. So our first question is, what is 1 3/8 times 8? Let's go back to our pizza example so we can kind of figure out, visualize this. Here's one whole entire pizza. That's the whole. And then we have 3/8 of this pizza. So this together represents our 1 3/8 of a pizza. So first thing we have to do is to get all of these as fractions. So we're going to convert the mixed fraction to an improper fraction. Improper means the top number is bigger than the bottom number. The easiest way to do this, if we're looking at 1 3/8, is to multiply 8 times 1, which is 8, and then add the 3, right? That gives us 11. So 11/8 is 1 3/8 as an improper fraction. This is the way we want to use it. So if we cut the whole pizza into 8s, we can see how many 8s we have all together, right? So here's our one whole pizza into 8 slices. Then we have these 3 additional slices of this pizza. So we have 8 8s here, 8, 9, 10, 11. So that looks right. That's what we had here, 11/8. That's the same number. So we're going to use that 11/8 in our next series of problems. So now we have to multiply by 3, because that was the problem, was 1 3/8 times 3. So we're going to look at our pizzas. Here we have 1 3/8 of a pizza, 1 3/8 of another pizza, 1 3/8 of a third pizza. So we have 1 3/8 times 3. What did we do in those other 2 examples with whole numbers? Put them over 1. So we have 11/8 times 3 over 1. So now we're going to just follow the other steps. 11 times 3 for the numerators is 33, and 8 times 1 is 8. 33/8. So let's look at another representation to see if we can kind of figure out if we're right. So we want to convert this to a mixed fraction, our 11/8. We don't want to leave it as an improper fraction. So here are our 1, 2, 3, 4 whole pizzas we filled with 8s, and we have 1 8 left over, right? So if we want to see what 33/8 is, we have 1, 2, 3, 4 whole pizzas. So there's our 4 whole pizzas. 4 times 8 is 32, with 1 little 8 left over. So now we have 4, right, and 1/8. This is what it looks like if we would just do it all without the pizzas. But the pizzas help you to see the picture. So we have 1 3/8 times 3. We made our 1 3/8 into 11/8, and we put our 3 over 1, right? So now we're going to multiply. 11 times 3 is 33. 8 times 1 is 8. And then we switched it up here to 4 and 1/8. That's our mixed number, right? Okay, so let's look at one more example just to make sure that we're doing it properly. Here's example number 2. In this instance, we have 2 mixed numbers we're going to multiply together. We have 1 1/2 and 2 1/5. Here's our answer, but how did we get this answer? Let's look and see how we got it. We want to change this 1 1/2 to 3/2, and this 2 1/5 to 11/5, right? Let's see how we do that step by step. We're going to convert our mixed numbers to improper fractions. So 1 1/2, we get 2/2, which is 1, right? And then we're going to add this half. So that gives us the 3/2. Because remember, when we added fractions, we moved the denominator over and added the numerators. So 2 plus 1 is 3. Same thing for 2/5. If we want to get 2, 5 divided into 10 goes 2 times. So that's 2, that's our whole number. And we have this 1/5 left over. So here's our 1/5. So we're going to add them just like we would normally add fractions. We bring our 5 over for our denominator. 10 plus 1 is 11. Now we can multiply. We've got our 2 numbers we need to multiply. So we bring our 3/2 down here. our 11/5 over here. 3 times 11 is 33. 2 times 5 is 10. So do we want to leave it in this representation here? Let's look and see if that's how we want our answer. We can convert that to a mixed number, right? So we take 10, how many times will it go into 33? 3 times, which gives us 30. And then 33 minus 30 gives us 3, and we put that back over our 10. So 3 and 3/10 is equal to 33/10. Our last example is 3 1/4 times 3 1/3. Let's make these into improper fractions, convert our mixed numbers. I did this the same way. 3 times 4, right here, is 12, plus 1 is 13. 3 times 3 is 9, plus 1 is 10. So we have 13/4 and 10/3. Now we can multiply. We multiply the numerators. 13 times 10 is 130. 4 times 3 is 12. But we don't want to leave it here. We want to convert it to a mixed number. So how many times does 12 go into 130? 10 times, which would equal 120. So if we take our 130 and minus 120, we get 10. So we put it up here, and then there, bring our 12 over. Can we reduce this? That would be our last step. Yes, we can reduce 10 and 10/12 to 10 and 5/6. That would be our final number.
Thanks, Miss Sinisi. All right, next up, we have an exciting reading lesson. Mrs. Easter is going to discuss how text features can help us become better readers. Let's check it out.
Hello, everyone. My name is Shanda Easter, and I am a teacher at Roe Branch Elementary and Middle School. And today I'm going to teach you about text features. So this is one of my favorite lessons to teach. And so to begin with, let's talk about what the term text features means. When you think of the word text, you may think of textbooks or magazines or even commercial advertisement. The next word, features, can be thought of almost like the features for each person. Some features that could describe me are brown hair and eyes, young, medium height, although you guys probably can't tell that right now. And if I gave features about, say, West Virginia, the list would include maybe winding mountains, low valleys, and steady streams. So with that in mind, when we put those two words together, we are able to look deeper into reading material to find out more information on the topics that we're researching or reading about. So now that we've got a better idea of what text features means, let's talk about what is considered a text feature. So what are text features? These include pictures, captions, labels, headings, and even table of contents, glossary, index, maps, bulleted lists, graphs, and even timelines. So basically, in other words, text features are things that stand out to your eyes when you're reading. And the author uses these features to bring attention to important information. Now that we have some background knowledge on text features, we're going to get ready for surgery. Today, we have a patient who needs some transplants. We're going to be finding text features from our magazines to carefully cut out and transplant to our critical patient's body. It is crucial to our patient's health that we attempt to find one example of each text feature listed. I think if we can find most of those, the patient will still survive. So let's get started. Okay, so let's go over what we've learned today. Text features helps readers find important information very quickly. They help us identify and remember big ideas and topics. They can be illustrations, headings, or even lists. So hopefully today you learned a little more about text features and how to use them in your next reading assignment or even assessment.
Thanks, Mrs. Easter. Okay, last but certainly not least, we have an awesome science lesson about transverse waves. Now, these types of waves are all around us. The Wi-Fi in our homes, the radios in our cars, and the microwaves in our kitchens are all examples of transverse waves. So for more on this topic, let's go visit Mr. Adkins.
Today we're going to take a look at transverse waves, an introduction. The topic we're going to be looking at is something that looks very similar to this. And a lot of people will refer to this as a ocean wave or any normal wave. This is what we normally think of, but it is often referred to as a transverse wave. A couple of things we're going to discuss first is what is a wave, how does it work, and what are some of the primary components of it. So let's take a look at what we're going to deal with first. Okay, looking at what we were discussing, the fact that we're talking about something called energy. So a wave transfers energy from one location to another location. Now, in our example here for this transverse wave that we're going to be discussing, it's going to require a medium. Now, a medium is something that allows us to manipulate the energy. So let's take a person. So let's just stand our person here, and let's give them a rope. Currently, the rope is not moving. Now, when the person raises their arm to a new location, then brings it back down to another location, the rope's going to go with it. We understand that concept. When we take a look at an example a little bit later on, we'll get it a little bit more in detail. So the first thing we're going to deal with is the fact that if the person raises their arm, our rope's going to come up to the high point. Then we're going to cycle it down, back up, back down, back up, back down. And when we look at this, this is our energy. So the movement of the arm is providing the energy. And the energy is going from the start location, traveling down the rope, and exiting the end of the rope. And that's going to be our transfer of energy. Now, our transverse wave gets its name from a couple about it. So when we talk about this wave here, we're going to give it a location. We're going to call this the equilibrium line, or this is when the rope is at rest and not moving. So as we look at that and we focus in on what's going on here, we're going to talk about some movement. Now, the movement of a transverse wave means that the energy transfers this direction. And our particles, or the rope that make up all of our little parts that move, go in this direction and this direction. The term that we're referring to here is the fact that these two objects make something called a right angle. And this right angle is referred to as perpendicular. So when we talk about a transverse wave, we're talking about the particles moving perpendicular to the direction at which the waves are moving. Now what we're going to do right now is we're going to take a look at a short video demo of a setup here I have that shows something called a standing wave. So let's get that set up and get it ready. Okay, the setup I have here is a piece of equipment from the physics class that I teach. So we're looking at the string that is moving. This object here is going to make moving up and down quite quickly. And what we're doing is developing something called a standing wave. That means that the wave goes all the way down to the end of the rope, hits the end, reflects back on itself, and creates the illusion that it is standing still. A couple of things that we need to remember. is that when we're looking at this area right here, it's called a node. That's the location that has the least amount of movement. This location here is called an antinode. It causes the most movement. Node, least movement. Antinode, most movement. So that was our standing wave that we created using the piece of equipment from our physics class. So we just saw that standing wave. So we're going to sketch that standing wave again. So the wave goes down, hits the surface, stops, reflects back on itself, and we get that kind of shape. Now, from that, we had a couple of items that we said that was our node. That was the location with the least amount of movement. We said this location here was the antinode, with the location with the most movement. So that was a node, and this was an antinode. Now, from those basic concepts, talking about the person moving the string to a demo of the string being set up, let's get into a couple of more details about a wave. So let's start out with sketching a wave here, and we're going to talk about the components of a wave, the parts. Now, we've got a couple of things here. Let's sketch in us a equilibrium line here to try to help us out. Ooh, it would help if I could draw a straight line, but that was close. Now, when we look at our equilibrium line, a location of the maximum movement above the equilibrium line is called a crest. Okay? The next location that we're going to be looking at is the lowest point below the equilibrium line. That location would be there. That is also referred to as a trough. Now, when we take a look at those, we have some basic ideas. Remember, the little green line was the equilibrium line. Now, when we take a look at this, we're going to zoom in for just a second here, and we're going to take a look at a specific location here. Now, one of the things that we're going to define is something that deals with this distance here. Now, that distance there is referred to the amplitude of a wave. Now, we're going to look a little bit more about amplitude and the amount of energy in a later video. So let's go on with a couple of more parts, okay, that we're going to look at. Let's sketch our wave again. Now, we're going to talk about something called a, whoa, that was pretty bad here. Let's undo that. Let's erase that last little part there. Okay, now we've got a basic wave. Now, we're going to talk about something called a wavelength. Now, a wavelength is a specific way of measuring a wave, and it refers to completion of one complete cycle. So if we pick this is my start location and this is my end location, you notice how I'm going from a crest to a crest. So that is completing one cycle. That would be one wavelength. Okay? So you can pick any location. So I picked this location here on my equilibrium line. So I'm going to go one crest, halfway there, come around the trough, end here. So that location from C to D would be one wavelength also. So when we talk about that, we have a lot of information that we can deal with. Now, these are some of the basics about a wave, specifically a transverse wave, and that's some information that we can use a little bit later on when we get to the effects of amplitude and energy.
Thanks, Mr. Adkins. All right, well, that wraps up everything for us here today on Education Station. We want to thank everyone who shared their awesome lessons, and we want to thank you for watching. We'll see you next time right here on Education Station.